How's it going? I'm Keon. I work at Clarify. Clarify is an artificial intelligence, like a machine learning artificial intelligence startup here in New York City. And I'm an applied machine learning engineer at Clarify. Been there since the summer of 2015, and I've loved it ever since. Today I'm going to be talking about convolutional neural networks, more so talking about the problem of computer vision. And what I mean is we're going to be talking about how to predict what is in a photo. So I give a computer a random photo, and then the computer can tell me, oh, I know what's in this photo. The way it's used to be done was people would manually figure out what the most important patterns were for certain concepts. So if I wanted to predict that there was a sunset, someone would say, okay, well, here are a bunch of like red pixels right by each other, and above that there are some purple pixels, and above that there are some blue pixels, and we think that's an important pattern for a sunset. And so for each concept you wanted to predict, you would like manually figure out important like patterns, but they didn't really work too amazingly well, and it was really arduous, really tough to do. So now we use computers to do this in a much better way. Instead of us telling the computer, here are the most important patterns, we have the computer just learn those patterns on its own. Now there's a lot more data, and we can use GPUs very efficiently. And so because of that, we can use convolutional neural networks. And the whole goal is we'll have a bunch of photos that are labeled already. Like we'll say these million photos have cats in it, these million photos have dogs in it. We're not going to tell it what makes it a dog. We just say this photo has dog in it. And we'll give a bunch of these photos to the computer, and it's going to find like similar patterns in all the photos that have dogs, all the photos that have cats, and it'll by itself say, okay, like these patterns are the most important patterns for photos that have cats or dogs, and so they can predict if a photo has a cat or a dog in it. The whole idea of a neural network is you have many layers. So each layer takes something as an input, has some kind of operation done to it, and then it has some output. The output of the first layer will become the input of the next layer, and so you kind of like have these multiple layers of inputs and outputs with some operations happening to them. In convolutional neural networks, there are three types of layers. The convolution layer, which is the key, pooling layer, and then fully connected layers. So what is a convolution layer? So to people, we see a photo, we see like a dog, cat, but to a computer, it just sees a big grid of numbers. It sees the RGB value for every single pixel. The computer is gonna try to find patterns in these numbers. And how does it do it? The first thing it does is it does a convolution. So for the entire like picture, it'll take a small little grid, and it'll say, okay, we're gonna times every number in this little grid by some other random number. This random number is like a filter or some pattern. An example of a pattern would be, let's say we wanted to have a line in that grid, like a curved line. In the grid will be a bunch of zeros and then a 1 for all the spots with the curved line. So you kind of have these little filters, and you apply it to the entire photo in every single possible spot, and you kind of move it over, move it over, move it over. And whatever you do some like matrix multiplication, and outputs one number. And so in the input, you have this huge photo. You do this convolution with many filters over and over again. And for each convolution, it'll output a single number, and then the next layer will just be a bunch of like features or a feature map of like what it represents is how prevalent these filters or these patterns were in the little grid of photos, in the little grid that we had from the photo before. That is what a convolution is. The idea is we're going to be over time learning what these filters are. Initially it'll be some random value, but we'll eventually learn what these little filters are. We then have pooling layers, which kind of just like summarize a big grid of photos. Let's say there's another grid within the photo, and the max value was, let's say, a 10. We then summarize, okay, all these four, we're gonna summarize these four by just one number, 10. And it kind of just makes the dimensionality smaller, and it makes computations easier in the future. And the last layer will be the fully connected layers, which you can kind of picture as a convolution layer, but a little tricky, a little different. A fully connected layer just has every input will be attached to all the outputs. Let's say you have these 5 inputs, and you have 5 outputs. So each of these 5 inputs will have a weight or a line kind of attached to all the 5 outputs. And so each of these weights will affect these outputs by whatever numbers in their weight. Before we had like a grid where we had a small little convolution happening and kind of shifting it over, we can now imagine a convolution that's like the entire space. That's a fully connected layer. The reason why we do these like convolutions is because if you think about photos, an individual pixel value doesn't matter. It doesn't matter if a pixel is green or blue or black or red. What matters is what a pixel's value is like in relation to all of its neighbors. So if a pixel is red and like its neighbors are like, if it goes purple above it and then Above that is blue. Like its actual neighbors are very important. There's like a lot of spatial context, and so that's why we use these convolutions in photos and videos. So how do we learn? We first have something called a cost function. What a cost function will do is it'll tell you how well your model is predicting. For example, let's say we have a photo and we know the photo has a dog in it, and we put it through our network, and our model's predicting like 0% chance of dog. That's pretty bad. We have a little error function that kind of tells us how bad we're doing. So the error is going to be really high if we're predicting pretty poorly, and it'll be very low if we're predicting very good. The cool thing about this function is we can take the derivative of it, and so we can know how different layers affect this error. So for example, we have this error function, we take its derivative, and we know now how much the last layer affects this loss, which is great because if we know how it's affecting it, we can kind of change it in a way to minimize the loss. And so we kind of change it a little bit to make the loss go down a little bit. We also know how much the second to last layer is affecting the last layer. With the chain rule, because of that, you know how much the second to last layer is affecting the actual loss itself. And then you can change the second to last layer to the right, to make the error go down a little bit. And you recursively keep on doing this for every single layer. It's like there's a bunch of dials that you're changing, and you're kind of like saying, okay, for this first layer, I'm gonna make the filter, instead of being this line, let's make it a little more curved, and you kind of like are having these little dials, you're kind of fixing every single layer. And it's learning it. It kind of, at first these filters are random pixels, now it's kind of like forming into something that's actually meaningful and important. And this is possible because we have a lot of data. I mean, with every example we put to the network, we say, okay, we know it's a dog, we can find our error and kind of keep on making it better over and over again with all these photos. When you're training these models, the structure is really important, yes, and also the more so important is the data itself. So you really want to have, of course, a lot of data, but your data, like the type of data is really important. For example, let's say I'm making a model that would predict like cat versus dog. And let's say all my training data, so the photos that my model will see and learn on, let's say all the photos that have cats in it also have like a tree in it. And all my photos of people have no trees in it. Because we're not actually telling the model like exactly what patterns to learn, it'll just learn whatever is in our training examples. And so, for example, if our photos have trees and cats in them, we're not sure if it's learning tree patterns or cat patterns. And so what'll happen is, if we have this case happen in practice, you might then show the model a new photo with no person or no cat and just a tree. And it might think, oh, this photo also has a cat in it because it's all the photos it was trained on also had cats and trees. You want to make sure whatever you're going to be predicting, make sure you're training on photos that are almost the exact same. So let's say you're making a model and you're going to be predicting like apparel stuff, like clothing. And I want to, in the end, I want to take a photo of someone and say, oh, this photo has a person wearing like a cool V-neck and like certain jeans and like boy cut jeans or faded jeans and that kind of stuff. And the end goal is to take photos of people in the real world. And let's say I'm training these photos like with photos of like just white background, like photos you'd see on like their like actual website, and it's like not in the real world. Because of that discrepancy, your model's not going to predict that well. There might not be certain patterns that would be there in real life and so on and so forth. And so you really want to make sure that what you're training on is like almost the exact same as like what you're actually going to be predicting on in the future. Yeah.